Hi, everyone. Sorry for holding you up for a delicious afternoon tea. My name's Jack. I'm a PhD student from the University of Auckland. My supervisors are Yunsing and Albert. And today I'm going to talk to you a little bit about my PhD work, which is on anomaly detection for maritime trajectories using continual learning. So an anomaly in a maritime vessel is defined as an unexpected change to its speed or heading. So an anomaly can indicate a whole range of different problems. It can indicate an oil spill, a change in course towards New Zealand might indicate a potential biosecurity risk. It could indicate illegal fishing activity. It could indicate a vessel in peril, or it could indicate that the vessel is changing course to avoid some sort of danger encountered at sea. So all of these things could present a danger to both the maritime environment or the New Zealand ecosystem. So the data that exists that must be equipped on vessels weighing over 300 tons at sea is called the Automatic Identification System, or AIS. So AIS is an automatic tracking system that uses transceivers on ships to provide vessel information. So these transponders may communicate with satellites or land-based base stations, or indeed each other. AIS transmits a variety of data, including the vessel's name, its call sign, the type of vessel it is, as well as its current latitude, longitude, speed over ground, or course over ground. So we're most interested in the data that indicates its geographic position. So we can use this AIS data to train a trajectory model. So in related work, in order to detect anomalies, they design models that first predict the most likely trajectory that the model is going to take. And then it compares that with the actual trajectory. And if the difference is very, very high, then this can constitute an anomaly. However, existing models do fail to account for a couple of different things. One is that vessels behave differently in different contexts. So we might expect a lot of movement in coastal areas, whereas in deep sea, we may expect a larger speed and for it to be traveling on a mostly consistent trajectory. They also fail to adjust to changing conditions at sea. This might be different shipping lanes or different boats that travel at different speeds. So we aim to resolve both of these problems. We want to allow a deep learning model to dynamically update according to changes in incoming data. So this means changes in shipping routes, and we also want to avoid forgetting previously learned concepts. While learning a new shipping route, we don't want to suddenly forget a very popular shipping route. Problem two is we want to train the model to detect anomalies in a range of different contexts. So an anomaly detected at deep sea is not necessarily an anomaly detected in a coastal region or a region that's popular for fishing, and vice versa. So expanding on those two problems, here are some ways that the shipping lanes at sea can change. They can change to avoid popular areas for whales. They can change because of geopolitical situations. For example, the war in Ukraine at the moment has caused changes to shipping lanes around that area. And global warming can cause some shipping lanes to change. So we want a model that can adapt to these changing environments. We also need our model to be context dependent. So we need it to predict different behavior in fishing areas, in coastal areas, and in deep sea. So in fishing areas, we expect that characteristic zigzagging pattern that may be the vessel laying nets. Coastal areas, we may expect a little more movement as it visits various ports. And for deep sea, we expect it to be a straighter line. So here is the model that we've designed. We use the underlying deep learning architecture of BiLSTM. So a lot of existing models use recurrence in order to take into account previous coordinates to predict the next few coordinates. So we use this to predict a trajectory, but we also introduce replay. Replay is a collection of previously stored examples from a particular region that is used to reinforce the model's understanding of a particular movement type in order to not forget it when it's training on new data. So we produce a predicted trajectory and then we compare it with the actual trajectory. We continue to update the model all the time, whatever we input. So the model is always changing. This is called continual learning. But we also get an output and we compare it with the actual trajectory. And now if the geometric difference is very, very high and exceeds a certain threshold, then we will classify it as an anomaly. So here are some results. That top one should be labeled mean squared error, so sorry about that. But our results indicate that TF-TSR by LSTM, which is our model, TF-TSR being the replay model that is overlaid on top of by LSTM, performs similarly in terms of trajectory prediction compared to existing state-of-the-art models. So our data for AIS was taken from the Gulf of Mexico for a 24-hour period on the 1st of this year. So we get our results in latitude and longitude, but we've approximated these to be coordinates on a sphere, which is accurate to 95%. So this is our results for the trajectory predictions, and now we have some results for anomaly detection. Now, unfortunately, we do not have a data set for ground truth in anomaly detection. We don't have any data sets that are labeled with anomalies. So all we can do is compare some of our anomalies with the anomalies detected by other models. So we have a couple of different types of anomalies. We have a course anomaly, which is just a change in course that is unexpected. We have a speed anomaly, so a sudden slowing in a vessel. And then we have a fishing anomaly, so fishing activity in an area where fishing is not anticipated. And that's a particularly interesting one for our model, because despite the fact that it is not a fishing area and it has been trained to detect fishing anomalies, it's not adapted like other models to the actual trajectory as it develops. So this is a good thing because it has a larger difference between the actual and the predicted trajectory. So an anomaly is more likely to be detected in that region. So in other regions that exhibit fishing activity directly, it will maybe display closer to the actual trajectory and therefore won't constitute an anomaly. So that's all for now. If we have time for a couple of questions.
Any question for Jack? Yes.
Short one. So, what would be the next step?
Absolutely. Well, it would be really good to have some ground truth and going through with humans to label certain anomalies. Another thing is to train it on a wider set of data. We've only trained it in the Gulf of Mexico. This is because that region has a lot of different activity, which is interesting to see. But we would love to have data sets that are closer to New Zealand, that have shipping trajectories in deep sea, and see how our model performs under that scenario. We'd also like to introduce a more evolution in the model itself. So when it's creating tasks, for instance, we would like those tasks to evolve over time. So tasks might represent certain regions of water for different contexts.
Thank you. Sorry, Bernard. Yep.
AIS does have the that data. in its transmissions, but it's not so relevant for detecting trajectories, so we discard it for this particular work. But it would be interesting to maybe use that as metadata to, for instance, say whether a vessel is classified as a cruise ship and it's doing something that looks like fishing, and then classifying that as an anomaly. So that could be another area of future work.
Very good. A quick, actually two from me. The quick first is AIS. It is some sort of a compulsory equipment for vessel, like the black box for plane. And the second one is actually how fast can you detect an anomaly in the trajectory, and how quick you can respond to it. I mean, like if it's illegal fishing, for instance, how quick you can warn the official for enforcement, for instance. Is it not too late into your prediction?
So for the first question, AIS is, from my understanding, a little sort of box with a monitor on it on board a ship, and it acts as a transceiver, so you can receive information from other vessels' AIS transmissions, and then you transmit it back to land or to a satellite.
And it's compulsory.
Yes, it's compulsory. So AIS pings every 2 to 10 seconds, I believe, depending on how close it is to land or whether it needs to ping to a satellite. It's compulsory for vessels that weigh over 300 tons, but I believe vessels can be fitted with AIS even if they're lighter. And what was the second question?
About the detection, the time that you can detect any anomaly for enforcement decision.
Yeah, so we trained it to predict the trajectory over the next 5 time steps. So generally, it will take at least a minute to have the required data to detect an anomaly.
It's quite quick enough. Yes.
Your table with results.
Yeah. So we used a variety of different metrics. They all constitute losses, so the lower the better. They all sort of represent, well, they measure the distance in geometry a little bit differently. So using just one would introduce bias. So we try and introduce a whole range. Yeah, transformer is strong for some of them, but there are a couple of reasons that we didn't adapt the transformer for continual learning. And one of the reasons is that it's quite slow. So it would take a lot of time to train on incoming data. And since we want it to be active all the time, yeah, it's better to use something like biosecurity. FT. That one is to do with just comparing the predicted minus the actual. So it doesn't calculate the Euclidean distance like a lot of the other metrics do. It just it's a little more abstract, I believe. Abstract, rather, I believe.
Thank you. You all deserved an afternoon tea.